I feel like a PC. I think I make it. Huh? I think I make it. Pretty light. Alright. Most of the people are from like no, I mean you probably
Did anybody have questions from the problem set for last night? Anybody have questions on that? I posted the answers to it on Drive, so if you need to just check your answers, you can check those and then let me know if you have questions. But those are available on Drive. So as you can tell from just the table of contents, we're going to be talking about slope and y-intercept. And this is something that should be pretty familiar to you from algebra. So hopefully this seems, things seem familiar. But we're going to be talking a lot about how do we interpret these things? What does this mean? What is it telling us about the pattern of behavior in the data? So we're going to start here with our least squares regression line. So normally we just call this the LSRL. Okay? Normally that's how you see it written. Whenever it gives you a question, it'll say write the LSRL for this set of data. So you just need to know that means the least squares regression line. In Algebra 1, you probably called this line of best fit. So it's the same concept. We just typically call it least squares regression line. That part, so I'm going to move it. Okay, so let me show you why we call it that. So let's say we have this data that we talked about in our terms Tuesday. If I wanted to fit a line in there that's going to fit as close as possible to our data, I want to fit it maybe right in there, pretty close. So if I draw this line in, then we have this one point is pretty much right on it, but the others are not. These other ones are missing hitting the line, but they're close to the line. Okay. Whenever we talk about this amount that it missed, when we talk about this distance here, that's our residual. Okay, so we talked about the residual is the difference between what actually happened and what we thought would happen. That actual and predicted difference, that's our residual. So whenever we look at this, we can find these residuals for each of these points is just that vertical distance of how far it missed. Whenever the line predicted, the line said, I think it's going to be here, but it was actually down here. The line said, I think it's going to be here, but it was down here. I think it's going to be here, but it was actually up here. So it missed it a little bit. What the least squares regression line says is I'm going to take all of these residuals and I'm going to square them. So it gives you this square of all these differences. And what your calculator is doing is it's finding all of these different options, because that may not have been the line. It may have been that the line was more like this, just off a little bit. Okay? It could be that it was a little lower here and a little higher here. The calculator is finding all of these different ones. It's finding the square of each residual and finding which one is the least square. So if it adds up the sum of the area of each of those boxes, it's trying to minimize those areas. That's what it's actually doing. That's why we call it the least squares regression line, because it's trying to make these squares as small as possible. So your residuals are as small as possible. Okay? So sometimes the name of this, you're like, what? Why are we calling it that? That's why. Because it's looking at all those residuals, squaring the values, and finding the minimum for all of them. Okay? So luckily you do not have to do that by hand. Your calculator is going to help you out. So that's the name of it. That's what it is. So when we write the equation, we're going to write it out as the y variable with a hat over it equals y-intercept plus the slope times the x variable. And that is typically the way we use it. In Algebra 1, you probably did y equals mx plus b. So this was in front of the y-intercept. If you write it that way, that's fine. It's just you're most often going to see it in this form. Okay, so if they give you the least square regression line, typically this is the order it's written. When you are writing this, we want to use context words or contextual words. For the x variable and the y variable, you want to write that in context of the problem. You will never write x and y. You will write what that variable is. Is this the height and weight? Is this the time and distance? Something like that. You're going to have variables for those. You would write it in those contextual terms. So whatever you would be labeling your x and y axis if you were drawing the scatter plot, those are the terms that you will use for the variable. And you always want to make sure you put this hat on there, because this shows that it's a predicted value. So if you forget to put the hat, typically you will lose points. So don't forget to put the hat. This shows us that whenever we look at our graph here, we have a prediction for where we think these points are going to be, but we're missing by a little bit. So we're predicting this value, but it was actually here. We're predicting this value, but it was actually here. So we can get close to the points using our predicted values, but we need to make sure we show this is a prediction. This isn't going to always give you the exact value. The only way you're going to get all of your points right on there is if you have a correlation of 1 where every point was on the least square regression line. That does not happen very often. So typically we're predicting a value and getting as close as we can. Questions on that? Hopefully this is making sense of what we've been doing. Okay, let's look at slope. So one of the things, as you probably noticed, and each time we calculate a value, we need to be able to explain what does that value mean in context of the problem. So slope is no different. We're going to have to write out a sentence explaining what does this slope mean. So typically you can say for every that's going to be, the things that I underline is where you're going to put it in context of the problem. So it may be for every 1 degree Fahrenheit, or for every calorie, or for whatever it is that we're doing. That's going to be our units in there. Increase in the x variable. And again, we would write that in context of the problem. What is our x variable in this problem? Y variable is predicted to and this is where it's going to depend on whether our slope is positive or negative, but we'll say it either increases or decreases depending on positive or negative. So you can pretty much use this sentence every time and just fill in those underlined parts with the context of the problem. One of the really important things, you need to have context. So all of these need to be in context. And we need this predicted to. We don't want to say the y variable will increase or decrease. We don't want to make it an absolute statement. We want to make sure that this is a prediction. It's not always going to happen. Many of the rubrics for grading this will have, if you leave out that predicted to or expected to or something to imply this is maybe going to happen, if you leave that out, it will knock it down a point. So it'll go from an E to a P or a P to an I. So you want to make sure that you're saying it's a prediction. Okay? That has to be emphasized. Okay, so how do we get the slope? We have a couple of ways, and then we'll talk about another way later. But today we're just going to look at 2 different ways that we can get the slope. First of all, if we have a table of values, we're going to start over here with this one. If you're given all of your data, then you would just do this way. So first thing you're going to do is enter the data. Into your L1 and L2. You're going to have 2 variables. So your X in L1, Y in L2 is typically what we do. Then you'll go to Stats, Help, and then number 8, then Reg A plus BX. When you do this, it's going to give you A and B, and you just plug those into your equation to write it out. So we looked at doing some of that yesterday, looked at some of that last week. Now we're going to look at what if they give you summary statistics. So sometimes they just give you information about the data instead of giving you the data. So if that happens, the slope is equal to the R value, so that's your correlation coefficient, times the standard deviation of Y over standard deviation of X. So you can remember this as you've learned slope all along. Rise over run, or change in Y over change in X is still standard deviation of Y over standard deviation of X. So it's still in that same order, numerator, denominator. We're just multiplying by this correlation coefficient. Good news is you do not have to memorize this formula because it's given to you on your blue sheet. So on the blue sheet, you'll see over here, this is on the front part, formula sheet. You'll see on this first column, this is the equation of the line. So it's saying b sub 0, they're calling that the y-intercept, and b sub 1 is your slope. So here's one of the formulas for b sub 1. We never use that one. This is the formula for the y-intercept we'll get to in a minute. Here's a formula for the slope. So there is that same formula that we just wrote down. So this is provided for you in your formula sheet. You just need to know where to find it and how to use it. Okay. All right. So they will give you all of this information. If they do not give you data, they will give you all of this. You just need to be able to identify it and plug it in. Okay, so that takes care of slope. Let's look at y-intercept. So, again, we need to know how to interpret. So, here we're going to say the y-intercept always happens on the y-axis. So it's when the x variable is 0, what do we think is going to happen with the y? Okay, that's basically what we're saying. So when the x variable is 0 in context. The y variable is predicted to be the y-intercept value. So that's the form of the sentence that you will use each time for interpreting a y-intercept. You're just going to say when the temperature outside is 0 degrees Fahrenheit, we expect the wind chill to be whatever. So that's how you're going to interpret it. If we're asked to calculate what the y variable is, again, if it's from a table, you're going to enter the data. The data in L1 and L2. Let's do stat count 8 and then red. And that will give us the A and B, just like it did up here for slope. And the A is going to be my y-intercept. B is your slope. Then if you're given summary statistics, then the y-intercept is equal to y bar minus the slope times x bar. And the reason this works out like it does, if we think we've got this formula is what they give us, okay? That's the form that we're plugging it into. Anytime you find the least square regression line, it always goes through the ordered pair x bar, y bar. So the mean for the x variable and the mean for the y variable is always a point on the least square regression line. Okay, that's always one of the ordered pairs that you can use to find this. So if we plug these in, so if we plug that in and we solve for y-intercept, that's how we get this formula. Okay? So for those of you that like to know, why does that give us y-intercept? That's why. Because this point is always on the regression line. So if we plug that in for x and y and solve for a, this is what we get. So that's where this comes in. Questions? Kind of hard to know what to ask until you actually try one, right? Okay, so what we're going to do, this goes on page 94 in your notebook. So that's on page 94. In your folder on, there should be a stations practice page. That's what is going to go on page 95. So I'm going to hand out the stations. I just made copies for each table to have all three stations, so you're not trying to pass them around and everything. So I'll come around and hand those out as you guys attach this into your notebook and get out your stations practice page.